Okay, we are continuing with paper 2, section B, Swiss Cottage 2014 Prelim. Section B is pretty straightforward as well, especially question 9. So question 9, as long as you read the graph carefully, you should be able to get the answer. I'm not going to go through part A and part B. Part C is your typical reasons why transformer are not ideal, refer to your book. Okay, I'm going to focus on your part D, the modification done. Now, if you are using a copper core instead of an iron core, a copper core is non-magnetic, meaning that your magnetic field lines will not be, that means your magnetic field line will not be squeezed into the iron core. Okay, that means if you use copper, it is the same as you don't use anything. Yeah, because it doesn't squeeze the magnetic field line into the core. And so your primary coil is actually not really linked to the secondary coil. What you'll be getting is that you have your coil here, your primary coil. Then let's say your secondary coil is here. Instead of getting a very nice magnetic field lines that is going through the two, you will be getting something like this. Okay, the magnetic field line will spread to both sides. So because of that, so you won't get an effective link between the two coils. Okay, modification 2, you are using a DC supply. Now, if you use a DC supply, you won't be able to generate an alternating magnetic field. And if you do that, that means your secondary coil will not experience any change in magnetic field line. Okay, but be careful. Don't just say that because there's no alternating magnetic field, there will not be induced EMF at the secondary coil. The reason of this is because even though you use a DC supply, the moment when you switch on, the secondary coil will still experience a short duration of magnetic field line changes, because it is going from 0 to something. So it will have some induced EMF at that particular moment when you first switch on the primary coil. And use the same logic. If you switch off the primary coil, again the secondary coil will experience, oh, there's magnetic field line, suddenly nothing, because you have switched off your primary coil. So your secondary coil will still experience something if you use DC circuit. So it is wrong to say that it is no induced EMF. The more accurate description would be, if you're using a DC supply, then there will be no alternating magnetic field, and without the alternating magnetic field, then there will be no continuous induced EMF on your secondary coil. So the keyword here is no continuous. Okay? Okay, question 10. Okay, question 10 is quite straightforward. If you look at this circuit, you will see that actually the circuit is not closed. And because of this bare wire, even if the circuit is closed, no current will want to flow into the variable resistor, because this path has very low resistance. So effectively you have basically shorted out the variable resistor. This wire is like a short circuit to it. Okay. Okay, when you look at your part B is quite straightforward. Basically these two things is connected in parallel, meaning that the voltage will be the same. What you need to do is that you need to find out what is the current first of the circuit. So what you need to do is that find the effective resistance. So you get it here, and then after that just use V equals to IR, because you know that it has 3 volts here, it's parallel. Okay, then they ask you to explain how it affects. Please remember that the brightness of the bulb is actually dependent on the power dissipation, not just voltage or not just current. It is power dissipation. Okay, so because the circuit is connected in parallel, so you can deduce that if this resistance goes high, then more current will prefer to go to your bulb. So when this resistance is low, more current, this resistance is low, then less current here. High resistance here, more current here. So you can use your formula, P equals to I square R, and then you can point out that when the variable resistance is having high resistance, then there will be more current going through the bulb. So basically you are saying that the more current flowing through the bulb, the brighter it will get. Okay, but please remember to also add that when the variable resistor is having 0 ohm, basically your light bulb will be short circuit and it won't even light up. So just add that line here and be very clear about the relationship. Okay, for part C I think it's too simple, so I'm not going to draw it for you. Okay, your question 11. Question 11, define the pressure. Please refer to your book. For your part 2, also this is a standard question. Refer to your book for the pointer. Please remember to mention that the molecules are in constant, continuous and random motion. You need to have all 3 key adjectives here. If not, you won't be able to get the full 1 mark. When you look at your part B, this is your standard pressure question. You are asked to find out the pressure caused by 250 mm column of mercury. So for this part of the question, you don't even need to look at the diagram at all. They just want to know how much pressure generated from here. So just use your ρGH, you'll be able to get your pressure. Okay, for your part B. Okay, part B, you need to analyze the diagram. You are asked to calculate the pressure from the flask. So what I usually do is that you need to have the understanding that if there is no pressure in the air flask, these 2 mercury level will be the same. Okay, but with this, then it is different. So you can choose any line. So for me, I will choose this line. I know that at this point on the line and at this point of this line, the pressure are equal. So if I call this B, I call this A, pressure at B must be equals to pressure at A. Okay, that is the concept that I need to have. So what is giving rise to the pressure at B is just your atmospheric pressure. Okay, if I look to the left, what is giving rise to the pressure at A will be the pressure from this flask plus this 250 mm of mercury. And I have this pressure from my part I. Okay, so with that understanding, you can form this equation here. So on the left hand side, I will have the pressure from the flask plus the pressure from the 250 mm mercury must be equals to the atmospheric pressure. So once you have this understanding, do your algebra, you can get your answer. Okay, for your C part I is your standard convection current description. So I won't go deep into it. Part 2. What will happen to the liquid level in the manometer? So when you heat this up, of course the pressure here will build and the gas will expand. So when this thing expands, it will pushes down the column on the left, and because it's incompressible, the column on the right will rise. So to get a more complete answer, please mention both the change in the right arm and the left arm. Okay? Okay, this is an interesting question. You are asked to find out what went wrong here. And if you look at this circuit, there's a lot of funny things going on. Number one, you can see that the switch is actually not on the live wire. So this is the first mistake the electrician has made. The second thing is that the passage here mentioned that the casing is actually metal. That means it's a conductor. If it is a conductor, then the earth wire must connect to the casing. So in this case, you can see that the casing is not earth. So that is the second mistake. Now the third mistake is that it is quite interesting. These two fans is actually connected in series. And if you look at it, if you just want to turn the fan A on, you can't do that, because even if you close this switch, the circuit will be open here. Okay, so meaning that fan A and fan B cannot be controlled by a singular switch. It's either you turn both switch on, then both fan on, or you can't do anything to it. So there are 3 errors. You can read it below. I'm not going to repeat. Okay. State and explain where you will put a fuse. Now, the stating part is quite simple, because we all know that the fuse must be on the live wire, just like your switch. Now, to explain that, you have to highlight that only if you put the fuse on the live wire, when the fuse blows, then the circuit will remain at 0 volt potential. Okay, if not, if you go and put the fuse on the neutral wire, yes, when the fuse blows, the circuit will stop working because the circuit is open, but the whole circuit will still be at 240 volt because it is still connected to your live terminal. Okay, so only by putting the fuse on the live wire, when the fuse blows, then the whole circuit will be disconnected from the 240 volt and therefore at 0 potential. So you have to highlight that in your answer. In part 2, it is quite straightforward. Just use your P equals to VI. You plug in the parameter, you will find that your current, your operating current required is 2.5 ampere, and your standard fuse is 13511. So you have to choose a fuse rating that is slightly higher, so 3 ampere. Okay, the last part, the electrician actually connect the earth wire to the live terminal in the socket. So what will happen is that basically the live terminal will make your metal casing live, and so when you're answering this question, please remember to address this part of the question. How does this pose a danger to the user? So don't just stop at, the live terminal is going to make the casing live. You have to relate your answer back to the user also. So remember to end your explanation with the consequence. When the user touch the casing, the user will get a shock. So you actually relate back to this danger word here. Okay, that will be the end of this paper. Thank you.